Beneath inland Queensland, in a place that's been mapped, drilled and studied for decades, geologists have just realised something they may have missed. Because this isn't a brand new basin, it's not unexplored territory, the rocks here have been known for years, tied into the massive Bowen Basin and Surat Basin system that underpins much of Eastern Australia's energy production. And yet, only recently, attention has snapped back to a deeper, less understood part of that system, the Taroom Trough, with the suggestion that it could become Australia's first new oil province in over half a century, which doesn't make sense at first. Because if the rocks were always there, if the basin has been studied, if hydrocarbons were already known, how do you discover an oil field in a place that was never really hidden? The answer isn't that the oil is new, it's that the understanding is. The scale of it is almost hidden in plain sight. The Taroom Trough is not a small, isolated structure. It's part of a much larger geological system tied into the Bowen Basin to the north and the Surat Basin to the south. Together, these basins form one of Australia's most extensive sedimentary packages, stretching across hundreds of kilometres and preserving a history that goes back more than 250 million years. But to understand why oil exists here at all, you have to go back to a time when this landscape looked nothing like Queensland today. During the Permian period, this entire region sat in a low-lying, swampy environment. It wasn't desert, it was dense with vegetation. Thick forests growing across broad floodplains and wetlands. Plants lived, died and were buried over and over again, building up thick accumulations of organic material. Over time, those layers compacted into what we now recognise as the Blackwater Group. At that time, it was just plant matter. But buried deep enough, given enough heat and pressure, that plant matter becomes something else entirely. The basin didn't stay still. Through the Triassic and into the Jurassic, it continued to subside. More sediment poured in. Sandstones, mudstones, entire sequences stacking up kilometre upon kilometre. Among them were key units like the Snake Creek Mudstone, rich in organic content, and the Precipice Sandstone, a porous rock that would later become critical for storing hydrocarbons. At this stage, everything needed for an oil system was being assembled, but nothing had actually happened yet. That came later. As burial continued, temperatures began to rise, slowly at first, then more significantly as the deepest parts of the trough were pushed further down into the earth. By the late Cretaceous, the rocks had reached temperatures high enough to trigger a transformation. The organic material locked inside the Permian coal measures began to break down, releasing hydrocarbons. This is the moment when the system switches on. The Blackwater Group didn't just sit there, it started generating oil, large volumes of it, and not just oil, but gas as well, depending on how hot different parts of the basin became. In some areas, conditions were perfect for liquid hydrocarbons. In others, temperatures pushed past that window, cracking oil into gas. But generation is only the first step. What matters just as much is what happens next, because oil doesn't stay where it forms. Once generated, hydrocarbons begin to migrate. Driven by pressure and buoyancy, they move upward through the rock, escaping the dense, impermeable source layers and entering more porous pathways. In the Taroom Trough, sandstones like the Precipice became these pathways, underground conduits that allowed oil to travel laterally for kilometres. This is where the system becomes dynamic. The oil is no longer tied to its source. It's moving, searching for somewhere to accumulate. And that means the location of oil fields has very little to do with where the oil actually formed. It all comes down to traps. Long before hydrocarbons ever existed in this system, the basin had already deformed. During the Triassic, compressional forces folded and faulted the rock layers, creating subtle structures, anticlines, pinch-outs, stratigraphic traps. At the time, they were just geological features with no obvious significance, but millions of years later, they became critical. Because when migrating oil encountered these structures, it couldn't keep moving. It became trapped beneath impermeable layers, accumulating over time into concentrated reservoirs. This is how fields like those associated with the Precipice Sandstone formed, not because the oil originated there, but because it was caught there. And this is where the Taroom system reveals its complexity. Geochemical studies show that there isn't just one type of oil here, but two distinct families. The dominant system is sourced from the Permian Blackwater Group, feeding reservoirs across a wide range of formations, including the Precipice Sandstone. This is the main engine of the basin, the system responsible for most of the hydrocarbons that have been identified. Alongside it is a secondary system, sourced from the Middle Triassic Snake Creek Mudstone. It's smaller, less significant in terms of total volume, but still capable of generating and trapping oil under the right conditions. So the basin isn't just a single system, it's layered, overlapping and interconnected. But here's where things start to fall apart, because not all of that oil is still there. In the northern parts of the trough, burial continued beyond the ideal conditions for oil preservation. Temperatures climbed too high, pushing the system into overmaturity. Oil that had already formed began to crack into gas. In some cases, hydrocarbons escaped entirely, leaking through faults or permeable pathways to the surface over geological time. The system worked, but it didn't stay intact. What's left in these northern areas today is mostly dry gas. The oil that once existed has either been transformed or lost, and this creates a misleading picture. If you only look at modern production, it can seem like the basin is gas-dominated, even though it originally generated large volumes of oil. The real story is more complicated, because further south, conditions were different. In the southern Taroom Trough, temperatures stayed within the optimal window for oil production. The rocks were buried deep enough to produce hydrocarbons, but not so deep that they were destroyed. Migration pathways were active, and crucially, the traps were already in place at the right time. This timing is everything. If traps form too early, they can be bypassed. If they form too late, the oil may already be gone. But in this part of the basin, the sequence lined up just right. Oil was generated, migrated, and encountered traps that are already capable of holding it. And not all of those traps have been drilled. That's the part that keeps geologists interested, because even though the system is old, even though much of the easy oil has likely already been found, the underlying mechanics suggest that more could still exist. The migration pathways were extensive, the trapping mechanisms were widespread, and the basin itself is large enough that it's unlikely every viable structure has been tested. This is not a new frontier in the sense of being unknown, it's a frontier in the sense of being incomplete. Modern exploration in the Taroom Trough isn't trying to prove that oil exists. That question has already been answered. Instead, it's trying to locate the remaining accumulations, the pockets of hydrocarbons that were generated millions of years ago and never escaped. And the government is both allowing and backing this kind of exploration. But in terms of exploration, it's a much harder problem. Because now you're not just looking for a working system, you're looking for parts of that system that survived. You're trying to find traps that were filled, sealed and never breached, reservoirs that retained their porosity, pathways that led oil into the right places without allowing it to leak back out. It becomes a question of precision rather than possibility. And this is where the Taroom Trough starts to feel familiar in a different way, because it behaves less like a single, obvious oil province, and more like a dispersed system, something closer to how mineral deposits are distributed. The oil isn't everywhere, and it isn't predictable at a surface level. It's controlled by structure, by timing, by subtle geological variations that determine whether a trap holds or fails. Which means the answer to whether there are new oil fields in Queensland isn't a simple yes or no. The system is there, the oil was generated, the pathways existed and the traps had formed. The only question is whether the right ones have been found yet. And in a basin this large, with a history this complex, it's entirely possible that some of them are still sitting there, unchanged since that moment they filled, hidden beneath a landscape that gives no indication of what lies below, quietly waiting for someone to drill into exactly the right piece of rock. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.